Um, okay, so now we're going to talk about ionic substances. So remember, ionic substances are those that have lost or gained electrons. So they're charged particles that are have gained or lost electrons. Remember that electrons are negative, so it always feels backwards. So if you gain electrons, you become negative, and if you lose electrons, you become positive. So just don't forget that. Okay, so here's the official definition. An ion is an electrically charged particle obtained from an atom or a chemically bonded group of atoms. We'll talk about that in just a minute, by adding or removing electrons. So again, we don't remove protons, we don't add protons because that changes the element, but we can lose or gain electrons, and that means the element stays the same. It's just charged or not charged. I think I already talked about this earlier in the slideshow, but that's okay. It's good to review it. So if an atom picks up an extra electron or electrons, it becomes negatively charged, which is an anion. We know that chlorine often gains one electron to become Cl negative. That's an anion, a negative ion. And an atom that loses electrons becomes positively charged, called a cation. And again, you can remember cation is the positive, looks like a T, a negative ion. An example is sodium. Sodium tends to lose electrons and becomes sodium ion. Now, again, we're not telling you why this is true. We haven't talked about that yet. By the end of the semester, you'll have a really good idea why. And you might already know if you've taken chemistry before, but if you've never taken chemistry before, you probably have no idea. But we'll talk about, eventually we'll explain why these things happen. But for right now, just kind of have to accept it. So cations lose electrons. And we're going to talk in just a minute about how we can predict what different elements will do. So predicting an ion charge. Having a periodic table, so that's why I say having the periodic table, and I don't know about teachers who don't allow you to use a periodic table. It's a tool and you can get so much from it. And if you want to write on your periodic table, now you'll have to use a clean, fresh one for a test, but if you have your periodic table and you want to write things on it, by all means, I'm happy for you to use it as a tool while you're studying. So the periodic table can often help us predict the ionic charge of main group elements. Now the transition metals are a little bit different, but the main group elements are pretty straightforward. So the main group metals, those will be the first column and the second column. Those are main group and those are metals. They will lose enough electrons to leave them with the same number of electrons as an atom of the preceding noble gas. So probably easier just to remember that group 1 likes to lose 1 electron. So they tend to form a +1 ion. Those in group 2 like to lose 2 electrons and form a +2 cation. So if you're looking at group 1, sodium, the noble gas before it is neon. Let's write that here. So let's look at sodium. Sodium has 11, sodium has 11 protons. It wants to have, so it has 11 protons and 11 electrons. It wants to have, the noble gas just before it is neon. Neon has 10 electrons, so sodium wants to try to have 10 electrons, so it will lose 1 electron. If you look at magnesium, which is in the next column, magnesium has 12 electrons, 12 protons and 12 electrons. It wants to be, again, like neon. And by the end of the semester, we'll say why that's true, but for right now, just remember that. So that's why it wants to lose 2 electrons, because it wants to have 10. So it's going to try to lose 2 to become, so the first column +1, the second column's +2. Now the nonmetals on the other end of the periodic table want to gain enough electrons to be the same as the next noble gas. So those in group 17 or 7A, depending on how you go for it. So if you look at fluorine, Fluorine actually also wants to be like neon because that's the next electron, the next noble gas after it. Fluorine actually has 9 protons and electrons. So fluorine actually wants to gain 1 electron to try to be 10. So that's why it forms a -1 ion. It gains 1 electron. And then those in group 6A or 16, something like sulfur. Let's do sulfur. Sulfur has 16 protons and neutrons, 16 protons and electrons. It wants to be like its neighbor argon, like the noble gas argon, which has 18 electrons. So again, it wants to gain 2. So it's going to become a -2 ion. I have a picture of that coming up in a minute. So again, here's more examples. So calcium has 20 protons, 20 electrons. It likes to lose 2 because it wants to be like argon. Bromine has 35 protons, 35 electrons. It wants to gain 1 electron because it wants to be like krypton, the next noble gas. Now, that should be underlined too, monoatomic ions. Rules for predicting charges on monoatomic ions. So again, just what I said, most of the main group metals will form cations with a charge equal to their group number. It's just another way of saying it. So group 1A will form a +1, group 2A will form a +2. And the monoatomic anions for nonmetals will equal the group number -8. So that's just another way of looking at it from the previous slide. There's 2 ways of looking at it. So like the sulfur, which has, it's in group 6, 6 minus 8 is -2. So sulfur will make a -2. Sodium is in the first group, so it's a +1. Chlorine is in the 7A, 7 minus 8 is -1. So we kind of switch on you, and there's the, because we have the A groups and B groups, and then we have the 1 through 18. That's why I like to use the A's and B's, because they kind of, some old things that work out for us. So these are just different. They're the same rules that I just talked about, but thinking of them in a different way. One thing to keep in mind is the metals, when we get to those stair steps, and I'll show you that when I pull up the periodic table. Even if they're in the groups 3, 4, 5, 6, the metals under the stair steps, I like to call them, they will tend to form positive charges, even if they're in, say, group 6 or group 7. So I'll talk about that in just a minute. So, for example, lead, even though lead's in group 4, it actually likes to make positive ions, and so it actually has 2 ions. Tellurium, which is in group 3A, tends to form 2 different ones. So we'll talk about those in a minute. But the main group elements, most of them are pretty straightforward. So here's what I was talking about. So all of these here in group 1A will make +1 ions. So group 1A, I think you can see my little dot, lithium +1, sodium +1, potassium, rubidium, cesium. They always form a +1. No matter what, these ions will form +1 charges. These here in the second group always form +2 ions. So group 1, group 2. Let's flip way over here on this end. So the noble gases never make charges because they're happy the way they are. The group 17, all make -1 charges, so they're 1 away from the noble gas. They all want to gain 1 electron. And here's where I talk about it. I kind of drew the stair steps in here. Above the stair steps, you can make these predictions. So the group 16 elements, or 6A, are -2. So oxygen, sulfur, selenium, tellurium, they're all -2. These in group 3A will form a -3 above the stair steps. This one actually, okay, no, okay. Now what I've done here is I've actually shown you, so the problem comes in with these transition metals. So notice that a lot of these transition metals, some of them only have 1 charge, zinc, cadmium, silver, but a lot of them have more than 1 charge. And this is slightly different from your book. I didn't like the way your book did it, so this would be a better slide to look at than the one in your book. Some of them are right, and some of them have more than 1 ion. So I didn't want you to use the one in the book. But I think this is a really helpful table, and we're going to talk about these transition metals in a minute. So you can kind of predict them, but you don't necessarily know which one it is. So there might be two possibilities, and so you can't predict the charges for these main group elements under the stair steps and these transition metals. But group 1, 2, 17, 16, and above the stair steps on 15 and 16, you can predict the charges. So to complicate things even more, we have other ionic substances. All the ones we've talked about so far are called monoatomic. Monoatomic meaning one atom. Chlorine, Cl negative, Mg plus 2, O negative 2, sodium plus. They're all single atoms. And those are the ones we've been talking about so far. It also turns out that there are many other ions that are actually groups of atoms that as a whole group have either lost or gained electrons. We don't know which element in the group, but as a group they've lost or gained electrons. And these are called polyatomic ions. So instead of monoatomic, polyatomic. Some examples, ammonium, NH4 positive. So as a group, it's lost one electron. The sulfate ion, SO4, as a group has gained 2 electrons. ClO4, as a group has gained an electron. This is often the downfall for a lot of students, so I would really take care learning this now, because they will haunt you the rest of the semester if you don't learn them really well now. Here's a chart. So I would be familiar with all of these. Let me go ahead and star the ones that you absolutely should know. You should definitely know ammonium, NH4 plus, cyanide. Carbonate is one that's very common. Carbonate, CO3 negative 2. Bicarbonate, not so much, but you probably want to know it. Acetate, it's kind of a weird one, C2H3O2. As a group, it's gained 1 electron. Hydroxide is a really important one. The chlorites are kind of hard. Hypochlorite, chlorite, chlorate, perchlorate. I would definitely know the perchlorate one. You would want to know chromate and dichromate. Cr2O7. So what I say knowing, I would know the name of it, and I would know the formula of it, and I would know the charge of it. I would just, if it were me, I would use flashcards and I would learn these, because I'm telling you they'll show up, and they're the things that tend to confuse people when we're doing compounds. They tend to really confuse people because the problem is, and you'll see when we start doing it, the problem is they have different, they're a group that have subscripts, but then we get other subscripts because they combine with other things. Permanganate, you probably want to know. Nitrate, phosphate, and sulfate. I would say these starred ones you should for sure know. I would definitely be familiar with these other ones. There may be some others that show up from time to time, in which case you'll be told them, but these it's assumed that you are familiar with, or at least can find where they are. And for a test, I would definitely know the starred ones. I will tell you, just to give you a heads up, when I give tests, I generally allow one index card with whatever notes you want to put on there. So if you're really bad at memorizing, you might want to put these on your card so that you can refer to them taking a test, because that's all you'll have. I won't put these on the test, but you'll be expected to know them. So, all right. So anyway, an ionic compound. So far we've kind of only been talking about molecular compounds, but now we're going to talk about ionic compounds. So what is an ionic compound? An ionic compound is one that's composed of positive ions and negative ions attracted to each other because of opposite charges. So probably one of our simplest ideas is, or the simplest ionic compound is sodium chloride. Na tends to form a +1. We just saw that because that's in the first column. Cl will form a -1 ion because it's in the 7th column. So we have a +1 ion and a -1 ion. They're attracted to each other, so they will come together and sort of stick to each other. They're attracted to each other, and so they will form NaCl. NaCl is an ionic compound. Now, I talked earlier about molecules, the molecular formula. It gets kind of confusing. Technically, molecular compounds aren't, I'm sorry, technically ionic compounds are not molecules. They're formulas. And I'll show you on the next slide why. Because the NaCl is like, it's not just one lone sodium attracted to one lone chloride. If there's a bunch of chlorides, they're all going to be attracted to a bunch of sodium. So what happens is they all come together to form this big unit, this big salt crystal. The ratio is 1-to-1 throughout, and so that's why we call that, it's not an actual molecule because they're all attracted to each other. So it's called a formula. So sometimes you'll hear formula, sometimes you'll hear molecule. Most of the time we talk about molecular weight or molecular mass. Sometimes you'll see the word formula mass. It just means the same thing as molecular mass, but it's for an ionic compound, and they tend to be kind of interchanged really easily. So anyway, NaCl is the formula for this ionic compound. So here's what I was saying. So we've got our, it's not just one sodium and one chloride. So like if you had let me draw it up here. So like if you had H2O, and you probably know what that looks like. We'll talk more about it later. H2O is an O attached to two H's. Well, there's one water molecule here. There's one water molecule here. There's a whole bunch of water molecules that are just individual. Whereas here, we've got one Na, one Cl, but then they're attracted to a bunch of others nearby. And so that's why the formula unit here is just one NaCl, even though it's not really a molecule. So that's just a difference, and that's just a difference in wording and nomenclature, but that's what it looks like. So it's different from a molecule where they're kind of all contained within one little thing. All right, so the key important point about ionic compounds. So we can have charged particles, but there's no such thing as me going to a cabinet and pulling out sodium ions. If they're a charged particle, they can't exist by themselves because they all will repel each other and go different ways. And so they can't exist by themselves. You can only have neutral compounds. So what that means is that our ionic compounds have to be electrically neutral. That means the total positive charge has to equal the total negative charge so that the overall charge for the compound is 0. So the easiest example is to see this again with NaCl. Na is a +1, Cl is a -1. So if I have one sodium and one chloride that combine together, they become neutral. So notice that when I write them separate, I have the charge listed. It's really, really important to have the charge because obviously Cl negative is different from Cl. Na positive is different from Na. Na represents the element. Na plus represents the ion. So it's absolutely important that you always write the positive charge or the negative charge or whatever it happens to be. But when you put them together in their compound, notice that we don't have the charges. Sometimes when I'm working, I might, kind of write them there. But in the actual, if you were given this as an answer, you wouldn't write the charges. You can sort of write them above it if you're trying to do work with it. But anyway, the compound put together is neutral. When we write the ions separately from each other, we put the charges. So what happens if we have a different charged particle? So what if we have calcium and fluorine, and they're going to form a compound? Well, notice if I put one calcium and one fluorine together, they're not going to cancel each other out because this is a +2 and this is a -1. And again, we can't have so if I put 1 and 1 together, you'd say, well, then that's a +1. +2 - 1 is a +1 overall. Well, you can't have charged particles just hanging out by themselves. They have to be neutral. So what happens in this case is we're going to need to have two F's because each F is negative. That will give me an overall -2 charge to balance the +2 charge. And so this is what my formula will look like. There'll be 2 fluorines for every 1 calcium. So just keeping this in mind, we've gone over the rules of the charges. Calcium will, you're like, well, here sodium's +1. It's in the first column. Calcium's in the second column. Calcium will never make a +1 ion to form 1 and 1. Calcium will always be a +2 ion. So it's not like we can say, oh, well, calcium, just give up one electron so you can form 1 and 1. That never happens. The charge is sort of set by the things in just by the fact, we talked about the noble gases. They want to be like the noble gases. And again, we'll talk about that later in the semester. But the idea is that calcium will always form a +2 charge. So when fluorine, which will never make a -2 charge, it will always only ever make a -1 charge because it's in column 17. The only way that they can combine happily is to have 2 fluorines for every 1 calcium. So let's look at some other examples. Sometimes we can use what's called the crisscross. So technically what we're doing is we're finding the least common multiple, right? So in that last case, we had calcium and fluorine. Well, what's the least common multiple for 2 and 1? Well, it's 2. How do we get a +2? We only need 1 of these. How do we get a -2 overall? We need 2 of those. And then these disappear when we stick them together. But notice what happened is we crisscrossed. So the -1, the 1 actually came down here, and the 2, without the positive sign, but with the 2 came down here. They kind of crisscrossed. So we can do that with this. Lithium's a +1, oxygen's a -2. So we need 1 of these and 2 of these. So we can kind of crisscross Li2O. So let's crisscross these. So if we have O is a -2 and aluminum's a +3. So what's the least common multiple? 6. So how do we get a +6? We need 2 of those. How do we get a -6? We need 3 of those. So we've crisscrossed those numbers. It doesn't always work. I'll show you an example in a minute, but let's do this one over here. Potassium is a +1. Phosphorus is a -3. So we're going to need 3 potassiums for every 1 phosphorus. So sorry, kind of blocks out what's there, but that's exactly what it says. Like I said, we want the lowest ratio. So let's look at this one, Mg2+ and O -2. Again, doesn't matter if it's the +2 or 2+. I think your book tends to put the number first and then the charge. There probably is a preferred way, but it doesn't matter as long as you have them both there. So, if you look at this one, the crisscross method doesn't really work because you would end up with Mg2O2. If you just look at it, you say, well, a +2 and a -2, they're going to cancel each other out. So MgO is the best answer. So, if you missed that and you did the crisscross, just take a minute, look at your final compound, and if there's if you can simplify it any, just sort of like a fraction, you're going to want to simplify it to MgO. 2 to 2 is the same as 1 to 1. So you always want the lowest ratio possible. So the crisscross doesn't always work, especially if you're not paying attention, but keep that in mind. It's helpful. Again, it's a way of getting what, the crisscross is just your way of getting your least common multiple. If you want, what's the least common multiple of 2 and 3? It's 6. You have to multiply the 3 by 2, and you have to multiply the 2 by 3. So that's where that's coming from. The least common multiple is 2. We need to multiply this by 2 and that by 1. So however you think about it, just the main thing is that they have to go in the correct formula to balance out the charges to make them neutral. Oh, there's my crisscrosses. Okay, so again, you want to make sure you have the lowest. So there, I just did that one. MgO is the correct answer. Now, like I said, I think those were pretty simple because those were all monoatomic. So here's where And again, I guess I'm going to highlight very heavily that you really want to know your polyatomic ions. You really want to know them, what their formulas are, what their charges are. Now, this is not so hard because we're putting them together, but in the next chapter, we're going to start, or the next 2 chapters, we're going to start pulling them back apart. So you kind of have to know what the charges are to be able to pull them apart and how many you have and things like that. But notice that here, you know, when you've got your polyatomic ions, those polyatomic ions do not change. They are what they are. There's always 1 carbon and 3 oxygens and a -2 charge. So a lot of times if you're doing these, you know, just kind of, it's that little 3 there that gets everybody confused, the little 4 there. So these polyatomics with subscripts of their own. But for right now, if it helps you to just kind of think of that as a unit, whatever it is has a -2 charge and you never change it, then you can sort of start to see the crisscross. So if I have a +3 and a -2, I need 2 aluminums and I need 3 of whatever this thing is that's -2. So this is how I write it. Make sure and put parentheses around all polyatomics because this 3 distributes among the whole thing. There's 3 of these whole things. Same thing here. Now in this case, but be careful. And I will tell you that especially as you're first doing it, if it helps you to put parentheses around it before you even do anything else, identify the polyatomic and you know, make sure that you don't change it. It is what it is. So notice here, the 3 comes down here. Now technically, there's 1 of these. We usually don't write a 1, and that's why there's no parentheses on this one, because the 1 just is assumed that there's 1 of those. But if it helps you, especially at the beginning, to write the parentheses and to put that there, it's not absolutely wrong. Here we've got a really complicated one because we've got 1 polyatomic that's positive and 1 that's negative. So we need 2 of these crisscross, we need 2 of those and 1 of those. So that's why it's written like that. If it helps you to see the polyatomic, go ahead and put parentheses around them. I think, like I said, right now this isn't super hard, but do be careful. And I also, especially this one, look out for. Let's say we want to do Mg and we want to do OH negative. This is also a polyatomic, so keep it together. So this is what it should be. It should be Mg1, OH, the whole thing 2. This means there's 2 O's and 2 H's, so 2 of those. A lot of times I'll see this, which what's the difference? This says there's 2 hydrogen and 1 oxygen. So notice that that would not be right. So be really careful, especially. I think it's pretty obvious to see this, that there's 3 of those things. But when it's the OH or the CN or one of those that don't have numbers in it, be really careful. So there's 2 hydroxides. All right. How do we name these things now? We need to name them. So there is a system, it's called nomenclature, how to name things. There's so many chemical compounds, we need a systematic method. Well, turns out that there's more than one systematic method for naming them. It depends on the type of compound that you're talking about. If you're talking about ionic, covalent, organic, different things. So there's different naming systems. In this class, we're going to learn 2 of them, and I'm going to work very hard to try to help you identify when you use one system and when you use the other. But, you know, I didn't make up the rules, so we'll have to blame someone else for that. But let's learn the rules. So like I said, there's two naming systems. So again, nomenclature is just a collection of rules for naming things. We know that compounds are identified by their formula, but they're also identified by their name. We're going to learn to name the 2 types of inorganic compounds. So organic compounds has its own nomenclature system. It is not anything you have to worry about right now. If you take organic chemistry, you'll learn that. That takes you all semester to learn that system. But we're only going to deal with inorganic compounds. So if we have organic compounds in questions or things like that, I will give you both the name and the formula. But if it's an inorganic compound and I just give you the name, it's assumed that you know what the formula is. Or if I just give you the formula, it's assumed you know what the name is because this is the system we're learning. So there's two kinds of inorganic compounds, as we've seen. There's binary compounds, which we've just been looking at. Well, there's ionic, that's what I should have said, ionic binary compounds. There are actually ionic compounds that have polyatomic ions, so not necessarily, so binary just remember means two. So like NaCl would be considered an ionic binary compound because it has two elements. Ionic compounds containing polyatomic ions would be like our Na3PO4, whatever. It's got polyatomic. So notice it's not binary because it has more than one element. That's a little trick for you. If you know it's an ionic compound and you see more than one element, more than two elements, that should be a trigger. Ding, ding, ding. There's a polyatomic in there. So I would have that. I have the polyatomic chart that you can print off as well. And so, you can start learning those. And if you see more than two elements and you're trying to name it, I would immediately look for your polyatomic ions because there's one in there. If it has more than two elements and it's not ionic, we're not learning how to name those. So that's a whole different course. The third category would be our molecular binary. So non-ionic, but only with two elements. So if it's got more than two elements, it's ionic, unless you're given the name, but you're asked to name, it's going to be ionic, polyatomic ion. So there's two different systems. There's the ionic system, which is one naming system, which is what we're going to do right now. Next. And then there's the molecular system, which is its own system. And we're going to do that last. Like I said, organic compounds have their own nomenclature system that will not be covered in this class, and you don't need to know that system. All right, so inorganic compounds are compounds composed of any other element other than carbon. So organic is carbon and hydrogen and a few others. And like I said, we can classify them into the ionic compounds, which can be either monoatomic or polyatomic, so the ionic compounds, and the molecular compounds. So I just got through saying that. I guess I have a second slide with all the same things on there. Molecular compounds, like I said, are from non-charged particles. These are things like CO2, H2O, blah, blah, blah. Our ionic compounds are things like NaCl, Na3PO4, etc. So ions, non-ions. How can you tell the difference? Our periodic table is very helpful. So now you know what the periodic table looks like, and you know where the dividing line, the stair steps between the metals and the non-metals. So in general, if your two elements contain, if one of the elements is a metal and the other is a non-metal, and they're combined together, it's ionic. So sodium is a metal, chlorine is a non-metal. If you combine them, it's ionic. Magnesium is a metal, chlorine is a non-metal, magnesium chloride would be ionic, so forth. So metal and non-metal. So if you have a binary system, you pretty much look metal and non-metal means ionic. What's the other kind of ionic compound? That would be generally a metal and a polyatomic ion. The only positive polyatomic ion is NH4, so that might throw you off a little bit, but mostly it's a metal and a polyatomic ion. So if you see a polyatomic ion, it's ionic, which is in the name. All right, now how do we name an ionic compound? We name an ionic compound by naming first the cation, the first ion, and then the name of the anion, the negative ion. So we need to know the names of the positive ion and the negative ion. So it's that simple, but let's drill down. How do we name the cations? Well, the monoatomic cations are just named after the element. So easy enough. The aluminum ion is just called the aluminum ion. The sodium ion is just called the sodium ion. So all of those in group 1A and 2A and aluminum, which is kind of its own thing, Magnesium would be the magnesium ion, and so forth. So monoatomic cations are named after the element. What happens if you have more than one possible charge for an element? Then what you have to do is use a Roman numeral. So if you have and those are those transition metals. So like I said, you can kind of refer back to that chart that I have earlier in this PowerPoint. Those transition metals, you can never predict what the charge is. And the sum of those under the stair steps in the main, like tin, lead, antimony, bismuth, tellurium, indium, you can't those you can't predict either. So if it's any one of those, if you know the charge, you actually name it with the Roman numeral. So you can see here, where's my picture? Here we go. Okay, so the cobalt +2, since it's not in group 1A or 2A, we have to indicate that it's the cobalt 2 ion. Cobalt +3 then is the cobalt 3 ion. With some other examples. Iron is in the transition, so there's an iron +2 and an iron +3. There is nickel, I think, let's see. Nickel can be a +1 or a +2. So all of those, and again, it's helpful to know which ones, but in general, you can remember transition metals overall, you can't predict. There are a few, so like aluminum, even though, no, aluminum is in the main group, so that's a +3. All the other ones below that, you can't predict. Everything below the stair steps in group 4 and 5 and 6, they can have different ones. There's a few, I'm just going to warn you. Zinc is always a +2, so a lot of times you won't get the Roman numeral. Even though it's a transition metal, you won't get the Roman numeral because there's only one ion. Silver is always a +1, so often you won't get the Roman numeral. If here at the very beginning, if it's in the transition, I will put the Roman numeral, even though it's technically not correct. So I'll help you with that. Technically, you won't see the name with it. If you put the Roman numeral, I won't mark it wrong. So just keep that in mind. I think it was aluminum, zinc, silver. There's one other one. Anyway, most of those transition metals have 2, so they need a Roman numeral. So if you know the charge, the name of it is just the Roman numeral. Now, the negative ions get changed. So, these positive ions are just called by, so either aluminum ion or cobalt 2 ion, cobalt 3 ion. The negative ions get changed. The stem or the suffix gets changed to IDE. And you're kind of familiar with that already, but, so Br negative is bromine. The element is bromine, but the ion is bromide. So it gets changed to the IDE. Let's do a few others. There's not many, so it's sort of helpful to just go through it. So like F negative is fluoride. Cl negative is chloride. I negative is iodide. Oxygen, -2 is oxide. So it's not oxygenide, but it's oxide. N -3 is nitride. S -2 is sulfide. Do be careful. S -2 is sulfide. SO3 -2 is sulfite. And then SO4 -2 is sulfate. So there's all kinds of different names that involve sulfur. So you just really have to take your time and kind of think through them. So anyway, P -3 is phosphide. Otherwise, if it's a polyatomic, it's just the name that you know. So like sulfate, sulfite, nitrate, acetate. The names are just the names, so that's easy. But the individual elements, ions, get the IDE ending. So now we just put it together. You put the name of the cation together with the name of the anion, which has the IDE ending, and we get the name of the compound. Some of them are very straightforward, like right here. So sodium, this is the sodium ion and the fluoride ion. So it's just sodium fluoride. Now, that's a good name because so the test is if you look at the name, cover up the formula again and see if you can take the name and go back to the formula. So sodium, because it's in the first column, is always a positive one. Fluorine, because it's in the 17th or 7A column, is always a negative one. So if I said to you, write the formula for sodium fluoride, you'd say, okay, sodium +1, fluoride -1, they go together 1 to 1, so NaF, okay? That's that straightforward. Now, MgO, same idea. Mg is in the second column, it's a +2. O is in the sixth column, 6A, so it's a -2. So it's just magnesium oxide. Again, you can double check yourself. Magnesium is always a +2, oxygen's always a -2. So if I told you the name magnesium oxide, you should be able to go back and figure out the formula. I've got a few others down at the bottom where you can see they might be different. But so far, we don't need Roman numerals because we don't need to know the charge of the positive ions because they're in the first column or the second column. Now, same thing here on the third one, potassium. Potassium's in the first column, so we know we don't need a Roman numeral. It's potassium 1. You might not have realized, but a little hint here is there's 3 elements, more than 2 elements. That indicates to you, should indicate to you that it's a polyatomic ion. So I would definitely have those, at least for the start, I would have those polyatomic ions printed off in front of you so that you could, or at least pulled up somewhere else so that you can recognize them. So this is the nitrate ion. So this is potassium nitrate. If you find yourself trying to give 3 different names, that means you are missing that there's a polyatomic ion. So it's kind of that simple. All right, now this one is a little bit more tricky. So let's start over here. So we know that's iron. And again, there's 3 elements, so there's a polyatomic. This is the hydroxide ion, so this is iron hydroxide. Now, Fe is in the transition, so you always want to have your periodic table and look and see where that is. Fe is in the transition metals. That tells me that generally speaking, it probably has more than one charge. And in fact, if I told you, if I covered this up and I said, write the formula for iron hydroxide, you'd be a little bit lost because even if you looked on that chart with the different charges, you'd see that there's 2 different charges for iron. So what that means is that this name has to have the Roman numeral because that's the only way that I can tell you what the charge of iron is as part of its name. Now, we didn't need the Roman numerals. Again, I didn't make up these rules, but we didn't need the Roman numeral for potassium, magnesium, sodium because you can just figure out what their charge is by looking at the periodic table. But iron, you can't. So you need to have the Roman numeral to indicate what the charge of iron is. Well, at first glance, you might say, oh, I have no idea what the charge is. You need to tell me. Well, keep in mind that it's in the formula. So a lot of times what you'll have to do is crisscross your formula. So that's why having the polyatomic sheet is helpful because OH is a -1. If you didn't know that, you would be looking it up. OH is a polyatomic hydroxide. It's a -1. There's 3 of them, so overall, the overall negative charge is 3. Because this is already balanced, that means that the overall positive charge has to be a +3. That means because there's only 1 iron, that iron is a +3. So this is the iron 3 hydroxide, the Roman numeral. In case you don't remember your Roman numerals, 1 is just a line, 2 is 2 lines, 3 is 3 lines. But remember, 4 is a line and a V. So this is 4 5 minus 1, and then 5 is a V. I don't think you need more than a 5, possibly a 6. VI is 6. I don't think you need more than that. Anyway, so this is iron 3 hydroxide. It's required here to have the Roman numeral, because if I just gave you the name iron hydroxide, you could not tell me the formula without knowing the charge. So that's why the name has to have the charge. This is the iron 3 ion versus the iron 2 ion. So silver chloride. Again, I would look on the periodic table. Silver technically is in the transition metal, so my rule would be to give it a Roman numeral. Now this is a funny one. Notice there's no Roman numeral. So again, I didn't make up these rules, but chemists in general don't put a Roman numeral after silver chloride, because silver, even though it's a transition metal, only forms one ion. Now, how are you as a beginner to remember that? I don't know. If you happened, in this case, if you happened to put a Roman numeral 1 on it, I would not count you wrong. The homework might, but I would not count you wrong on a test. In fact, and how do I know it's a 1? Because Cl is a -1 and Ag then has to be a +1 because they're 1 to 1. So you could put the Roman numeral and kind of go by that rule that all transition metals should have a Roman numeral, but just saying that you probably won't see it out in the real world, because if you look at that sheet that's a few slides back where it has the different charges, you would see silver only has 1 charge, so you don't need a Roman numeral, but it's just too many exceptions to the rule to make it difficult. All right, now here, mercury, notice that these are both mercury oxide, right? Mercury oxide. Hg is mercury. So again, mercury, I can't spell. Clearly we need a Roman numeral here, because we have to be able to distinguish between these two, because they have to be different charges because they have different formulas. Now, just in case you're wondering, there are some older fashioned names, like there's mercurous and mercuric, and same thing with iron. There used to be something called ferrous and ferric. You may still run into some of those, like ferric is the +3, ferrous is the +2. We are only going to do the Roman numerals. So you need to learn the Roman numerals. If you were to Google something and use the old-fashioned name, I would not count it right, even if it is right. So we're only learning the Roman numeral numbers. Some of those old ones are really confusing. Anyway, so this will be mercury something oxide, and this will be mercury something oxide. So how do we know what the Roman numeral is? Again, we're going to have to pull them apart. Now, at first glance, somebody who's new to this might just say, oh, well, it's mercury 1 because there's just one of them. The number doesn't matter. It has to do with what its charge is. The Roman numeral, again, means its charge. So you really have to stop and think, what's the partner's charge? Well, oxygen in this case is a -2. It's in the 6th column. So if oxygen is a -2, in this case, mercury has to be a +2. So this is mercury 2 oxide. So be really careful. Take your time. Be really careful with that. This is a mercury 2 oxide. This one, again, because there's only one oxygen and it's a -2, that means that the overall positive charge is a +2. Because there's 2 of them, each one is a +1. So this is mercury 1 oxide. So it's actually almost a little backwards from what you might at first imagine. So this is mercury 1 oxide, and I forgot to pull that down. The silver is a transition metal. Anyway, so mercury 2 oxide, mercury 1 oxide. Let me give you let's do one more example over here. Let's say we have cobalt phosphate. These might not be real, but anyway, again, here's two different cobalt phosphates. So cobalt phosphate, but we definitely need the Roman numeral because we need to know what the charge is. So you may not recognize that phosphate is a -3. The phosphate ion is a -3. Again, I highly recommend just learning these. The quicker you know them, the easier all of this will be for you. Phosphate's a -3. So that means overall the overall positive charge has to be a +3. Since there's 3 cobalts, each one is a +1. So this is cobalt 1 phosphate. Here, you can kind of uncrisscross sometimes. You can't always, but we could have uncrisscrossed. There's 1 of those and 3 of those, but they don't, like I said, they don't always work. So you just kind of want to be careful. Here, each phosphate is a -3. So overall, the total charge is -6. That means the total positive charge has to be a +6. And since there's 3 cobalts, each one is a +2. So this is cobalt 2 phosphate. So anyway, you need to practice a few of those. I think we got on the next slide, we've got a few practices. Yeah, so let's do these. So Li is lithium, O is oxide. Lithium's in the first column, so it's a +1, oxygen's a -2. So this, you don't have to worry about Roman numerals because lithium's in the first. That's all you need to know here. So this is just lithium, so lithium oxide. Chromium is a transition metal. It's in the transition, so we're going to need a Roman numeral. ClO4 is the perchlorate. Perchlorate happens to be a -1. There's 3 of them, so overall the charge is a -3. Let me write this here. So each one is a -1. Overall it's a -3. That means the chromium has to be a +3, and there's only 1 of them, so the whole thing has to be a +3. So this would be chromium 3 perchlorate. I think this one was on the previous slide. Potassium and nitrate. Potassium's in the first column, doesn't need a Roman numeral. The reason why I don't want nitrogen and oxide, I want nitrate, which is a polyatomic, because there's three elements here. I know there's a polyatomic in there because we're talking about ionic compounds. So potassium nitrate. All right, sodium, again, that's good, no Roman numeral because sodium's in the first column. What is SO3? That wasn't one of the starred ones, but it's sulfite. So this is sodium sulfite. Cadmium. Cadmium is it's in the transition metals, so we don't know what its charge is. We need to indicate its charge with a Roman numeral. Cn is cyanide. Cyanide. Each cyanide is a -1. There's 2 of them, so cadmium has to be a +2. Cadmium 2 cyanide. Here's one with our positive. The Br is bromide, NH4 is ammonium. Ammonium is just what its name is, so ammonium bromide. This one's kind of similar to the one on the previous slide. Mercury sulfide. Sulfur is a -2, so mercury has to be a +2. So again, make sure you know what the charge is here. So mercury 2 sulfide. Even though there's only 1 of them, the charge is a +2. All right, here's another one. If it helps to put parentheses around the polyatomic, this is dichromate. The dichromate ion is a -2 ion, so that means the iron is a +2, so this would be iron 2 dichromate. Okay, so we're nearly at the end of this chapter, but now we're going to switch gears into the non-ionic compounds. So let's just refresh. Binary just means 2. So binary compounds only have 2 elements. So this will get rid of any of those polyatomic ions. So if you have a polyatomic, we know it's ionic. So the only two that you have to distinguish between are the metals and the nonmetals, or the whether it's a metal and a nonmetal or two nonmetals. So a binary compound is a compound composed of only two elements. Binary, of course, just means two. Now, if the binary compound has one metal and one nonmetal, those are the ones we've been doing already. Those are ionic compounds, and they're named using the ionic compound rules that we just went through. So that was our example, MgO. MgO, that's a metal and a nonmetal. NaCl, that's a metal and a nonmetal. MgCl2 would be a metal and a nonmetal. So those all use those ionic, magnesium oxide, sodium chloride, magnesium chloride. Those are all the the rules that we've just been learning. Now, the system, notice that even though I have two chlorines here, I still name it, let's go down here, magnesium chloride. I didn't tell you how many chlorides there were. I just said magnesium chloride. It's up to you to say, well, magnesium's in the second column, so it's a +2. Chloride's in the 7th column, it's a -1. So when I put them together, there has to be a 2 here. So nothing in the name actually tells you how many there are. It's all in the charges. And this is where, if I made the rules, I might change them, but these are the rules, so you kind of have to learn them. So again, notice that we're not indicating how many. The only thing we indicate is like we said earlier, like HGS would be mercury 2 sulfide. So this is not telling me how many there are, but what the charge is. So this tells me that the charge of the mercury is +2. Since sulfur is -2, that's why it's 1 to 1. So just keep that in mind. All of this naming system that we just learned, we don't actually ever tell how many of each element there is. We just only need a Roman numeral to indicate charge, or no Roman numeral if it's in the first or second column. Okay, so the other kind of binary compound, so like I just said, the ratio is set, and there's no indication in the name of how many of each there are. The other binary naming system that you need to know is when there are two nonmetals. So there's fewer of them because we know that the nonmetals are above the staircase. So there's not that many nonmetals. So but just keep in mind that these are all the elements. If there's two nonmetal, if there's no metal involved, then you're going to use this other system, which is called the prefix system. So these are molecular compounds, not ionic compounds, and we use a different naming system. So it's really important to keep these two straight, because right now we're keeping them separate, but I'm going to mix them up for you. So this is how you know. Two nonmetals uses the prefix system. A metal and a nonmetal is ionic. So the prefix system actually does tell me how many different of each element we have. And this is because, like I just said, with the ions, we can easily figure out how many go together by knowing their charges. We know, even though magnesium chloride doesn't tell me there's two chlorines, I know that because magnesium's a 2+ and chloride's a -1, I know that it's a 1 to 2 ratio in the formula. In this case, there's nothing to tell me that because there's no ions, everything just links up. We can actually have different ratios. Here's an example. CO, CO2, C2O3. There's different ways that we can put C and O together. Both of these are nonmetals. Similar, so right there, and when we've got nitrogen in there, we could have NO2, we could have N2O4, we can have all kinds of N2O5, we can have all kinds of different ratios. Because they're not ionic, they can combine in different ways. So we have to explicitly indicate how many of each there are in the name, because we can't predict it by looking at the periodic table. So that's what the prefix system is for. So Here are the prefix numbers, and they're numbers that they're terms that you've probably heard before. So 1 is mono, 2 is di, 3 is tri, tetra, penta, hexa, hepta, octa, nona, deca. Those are the Greek prefixes. So if we have a binary molecular compound, and how do you know if it's molecular? It's because it's 2 nonmetals. Remember, if there's more than 2 elements, it has to be ionic because there has to be a polyatomic, because we're not naming we're not learning any of the naming system for molecular compounds with more than 2. So just keep that in mind. So what we do is we name the compound. The first one, the name of the compound has the elements in the order given in the formula. Generally speaking, the first one is the most metallic, but don't worry about that. They'll pretty much be in the order given. So you just name the first element using the exact element name. And sometimes this can be confusing because sometimes some of the IDE, like chlorine, could be listed first, or bromine, or sulfur. So we don't change the first one to IDE, even if in an ionic compound it might be an IDE. So the first element is always just named exactly as it's written or found. And then the second one will get the IDE ending. But we have to use a prefix to indicate how many of each element there are. So if there's more than one atom of any given element, you have to add a prefix. So let's look at some examples. So SF4, sulfur tetrafluoride. If you don't know which system to use, find sulfur, find fluorine. They're both nonmetals, so we need the prefix tetra because we don't know. And let me just say, sometimes they can make ions, so it does get very confusing. But notice that both sulfur and fluorine, if they're going to make ions, are both going to be negative. So they can't go together in ionic compound. They have to be a covalent molecular compound. So that's when we use the prefix. So sulfur tetrafluoride. ClO2. Chlorine, notice the first one gets the regular name, chlorine dioxide. Sulfur hexafluoride. So sulfur hexafluoride is different from sulfur tetrafluoride. Cl2O7, again, dichlorine. This is not the polyatomic ion. This is the compound, dichlorine heptoxide. It doesn't have a charge or anything. Do note that if the first element only has one atom, generally we don't use mono. So like, see, we didn't put monosulfur tetrafluoride. Now technically that wouldn't be wrong. Monosulfur tetrafluoride, monochlorine dioxide, we don't put mono if the first one's mono. Actually, we don't always even use mono at all, except sometimes it's put in explicitly. So for example, CO2 is carbon dioxide, but CO is carbon monoxide. Technically, if you said carbon oxide, this is what you would be talking about because the monos would be left off, but just for emphasis, we put mono. Do note this one, if there's 2 vowels adjacent, we generally drop the A. So it would be, the A and the prefix, or the O or A and the prefix. So monooxide, we don't say monooxide, we say monoxide. Dioxide. If this was oxide, it'd be hex oxide, not hexaoxide, but you get the hept oxide. So that's just a minor thing. If you put the A, I wouldn't count it wrong. So here NO2 is nitrogen dioxide. But don't forget, if the first one has a number, you do need the prefix. So this would be dinitrogen pentoxide. So these are not hard. I think the only hard thing is knowing which system to use. So again, this system is only used when both elements are non-metals. If there's more than two elements, it's not going to be a binary molecular compound. It'll be ionic with a polyatomic. Doesn't mean they don't exist. It's just we're not learning the names for those. That's organic chemistry, and we're just not dealing with that. So those would be, you would be given the name. So the only ones you have to know are these binary ones. All right, just a few other little topics to tie everything together. So acids, we just, again, we'll learn more about acids later in the semester or later in the year, but let's just talk about some of the names because they come up a lot. So acids are traditionally defined as compounds that are ionic that have H plus as the positive ion. So you know, we have NaCl, which is a salt. HCl then would be an acid because the positive ion is H. H2SO4 is an acid. HBr, HNO3. Those are all, so if the positive ion is at H, they tend to be acids. Now, there's kind of a funky naming system for acids. I really don't expect you to get into it too much. But so there's actually just a few that I want you to know the names of. So that's what we'll go over here. So with a binary acid, again, binary 2 consists of hydrogen and one other ion. So like HCl is considered a binary acid, HBr. Now technically we know how to name this: hydrogen chloride, hydrogen bromide. But if it's an acid, we tend to give it a different name. So it actually changes. We end up saying hydro and then chloric acid. Now technically HCl is hydrogen chloride. That's usually a gas if it's dissolved in water, so often you'll see aqueous. That's hydrochloric acid. HF, hydrofluoric acid. HI would be hydroiodic acid. Hydroiodic. And then HBr would be hydrobromic acid. H2S would be hydrosulfuric acid. Don't worry about the H2S. So I would basically know the HCl and the HF, maybe be familiar with these other two. Now oxoacids tend to be acids that have one of the common polyatomics. So that would be like H2SO4, HNO3. Those are a little, well, they're a little bit easier, but we don't do like hydrogen sulfate, hydrogen, we use different names. So here's the ones that you should know, you should be the most familiar with. I'll tell you the names of any others. If you have the hydrogen with the carbonate ion, it becomes carbonic acid. If you have a hydrogen with the nitrate ion, it's nitric acid. The phosphate ion becomes phosphoric acid, and the sulfate ion becomes sulfuric acid. Again, there's others. If it's the sulfite ion, it becomes sulfurous acid. There's lots of names, and the system is kind of screwy, but I just want you to know, probably I would say these 6 acids you should know the names and formulas for. So don't worry about the naming process so much. So again, here's hydro. So here's the again, the ones I just went over. So I would know the top 2 common simple acids, and then like I said, here you should probably know acetic acid also. So the hydrogen with the acetate ion is acetic acid. The nitrate ion, so I would know that one. The nitric acid, the carbonic acid, and sulfuric acid, and phosphoric acid. So I would know those 5. This can't help to know these, but the nitrite becomes nitrous. The perchlorate becomes perchloric, sulfite. So anyway, I would know those. And up here, I would definitely know those, and maybe this one too. Okay, one other little topic is a hydrate. A hydrate is a compound that contains water molecules. A lot of times what happens is you have these crystals, these salts that have water molecules associated with them, bounded into their crystals. And I just want to introduce them to you because we'll come across them. If the hydrates don't have the water associated, they're considered anhydrous and they're dry. But if they have water next to them, they have the word hydrate, and the prefix indicates how many. So let's just do a few examples and it makes more sense. So this is how you'll see a hydrate written. So it's got this dot. It doesn't mean multiply, it just means they're attached to each other. So here we just named this compound. So this is copper sulfate. Now it's copper 2 sulfate because copper is a transition metal. Sulfate is a -2, so that means copper has to be a +2. So that's copper 2 sulfate. And now there's 5 waters associated with it, so we just would call that pentahydrate. So if you see that dot with the number of waters, you just name how many hydrates are with it. We're going to do a lab dealing with hydrates, so hopefully it'll make more sense then. So let's look at what you need to know for this chapter. It's a long chapter, lots of operational skills, what you should be able to do at the end. So you should know the postulates for Dalton's atomic theory and what they tell us. Be able to kind of go through the different the modern atomic theory. So basically the names and what they discovered. So, you know, Dalton was the first one to say the atom was the smallest particle, and then J.J. Thomson discovered the electron, and then Millikan and all the rest, what they added to it and how the atom evolved. Right, so again, knowing into how the results were interpreted. You don't need to know all the details, but mainly what this person kind of discovered and what that told us about the atom. Know the 3 subatomic particles, where they're located, what their relative charges are, and their relative masses are. You want to know what isotopes are and give examples for several elements. Be able to interpret symbols. So in other words, you want to be able to use those nuclide symbols so you can figure out what the atomic number is, the mass number is, what the charge is, how to figure out how many protons, neutrons, and electrons there are in a particular nuclide. Know the difference between atomic mass and average atomic mass. That's not what that says. I know. Define atomic mass unit. Atomic mass unit, you don't have to remember the number, but it's basically the relative mass of one proton or neutron. So what is the average atomic mass? So the main thing is you want to know what the average atomic mass is and how that's different from the mass number. The mass number, remember, is for an individual element and individual isotope that has a certain number of protons and a particular number of neutrons. And then the average atomic mass is the weighted average of all the different isotopes with respect to their abundance. So you should be able to know how to calculate an average atomic mass by given its isotopic abundance, or be able to tell at least which isotope is more abundant if you're given the average. Okay, so being able to calculate it or being able to predict it. Be able to know how to write molecular formulas, and empirical formulas. Don't worry so much about the structural formulas that's in there, but you can be able to identify it, but we're not going to be drawing those yet. Know what the periodic law is and how kind of know the organization of elements on the periodic table. I don't know that you have to predict the general properties, but just the ones that were listed in this. So knowing that knowing the names. The halogens are very reactive. The noble gases are not very reactive. The alkali metals, So kind of based on their, which ones are metals, which ones are nonmetals, which ones are metalloids. Define ionic and molecular compounds. So, ionic compounds are those made up of two ions. Molecular are covalent bonds that are, ionic is a metal and a nonmetal, or a metal and a polyatomic ion. Molecular are two nonmetals. So being able to predict the type of compound based on their location, what I just said, determine the formulas for simple ionic compounds, be able to name them, including Roman numerals, and be able to name the ionic common types of inorganic compounds using the systematic approach. So knowing the difference between the ionic naming system and the molecular naming system, and being able to name ions and being able to name using the prefix. So it's a lot in this chapter, but you can do it. Okay.